Okay, so last class we sort of left off and somebody just wanted to go over it. So whatever, we'll just get the ball rolling while talking about the swern, right? And so the sort of swern oxidation was the alternative to PCC when you're taking a primary alcohol and you're trying to take an aldehyde. A somewhat quote unquote greener method is to use the swern oxidation, which takes DMSO. Right, so that's basically DMSO. Some chlorinating agents, so the classic is oxal chloride, but we learned thionyl chloride, so we'll just stick with thionyl chloride to stay consistent, right, which is, right, and then triethylamine, which is an amine base. Now, one of the key things, I don't know if I brought up last class, I've been meaning to, is we're going to see triethylamine every once in a while, okay? And these sort of tertiary amine bases, or things like pyridine or so forth, right? So these bases that are sort of neutral, that become protonated during the course of the reaction, you will occasionally be tempted to use them to, say, for example, deprotonate an alcohol. It's unclear that that's actually the mechanism that's going on. I may be somewhat forgiving in certain mechanisms, but in general, you know, the way that I always think about the amine, as we'll see through this sequence, is that it sort of soaks up the HCl. So a lot of times you're generating some acid, like pretty strong acid, and the sort of the base in there is basically almost buffering the reaction to make sure that you're not generating HCl. And so we'll see that we'll have, like, for example, chloride ions in this reaction that could in principle serve as a base, but then we'll generate HCl. So in those instances, the triethylamine will generally come in here and serve as the base. And so what I mentioned is that I think the first step of the swern is one that's sort of formation of the active reagent, which is to basically take thionyl chloride and react it with DMSO. This is chlorination reaction. This is analogous to what we saw with alcohol chlorination, right? And so we'll see in carbonyl chemistry that we push up electrons on their carbonyl, so sometimes you'll see people do that. This is actually a tetrahedral carbon. It's not an sp2 carbon, tetrahedral sulfur. It's not an sp2 sulfur, which is kind of weird to think about. So again, if it's confusing, don't worry about that too much. But the point is that this is a little bit different with sulfur than it is with carbon. And so the actual mechanism, you don't actually have to go up into the carbonyl, although sometimes I'll even do that just by habit, right? Because we're so used to doing, as we'll see, a lot of the chemistry with the carbonyls will push electrons up there. But you don't need to for this one. We'll lose our chloride. All right, then we'll have our Cl minus. Right, and what's going to happen here is the chloride's going to attack, just like it would in a chlorination reaction. We're going to generate SO2 gas. Plus SO2 plus Cl minus. Right, so this is the sort of first step of the swern. This sort of reagent that we see here ends up being important for the swern reaction. Okay, so now what's going to happen is the alcohol is going to react with this, and this is the part of the reaction that's a little bit, I think, certainly uncomfortable for me when I draw this. I've struggled to find a better way to do this, and online you don't find much help, although you find statements that I'm not necessarily sure I 100% agree with. But I'm not necessarily an expert on the swern mechanism. But usually the mechanism that I draw, I just deal with it, although you'll find in the book that they'll just try to avoid this by shorthanding. I won't shorthand, but I'll point out why this may be a bit uncomfortable for you guys. And I'll also point out why the alternative is also fairly uncomfortable for me. Right, and if you're looking at that molecule, you probably know already why I don't like this structure that much, and it certainly should feel not something that we generally like to do. right? We've got this molecule that kind of has two positive charges on adjacent atoms. And if you look online, which I have to try to find a better mechanism for this that might help me a bit, they avoid this altogether by just showing that mechanism and then just leaving out the proton. But I don't want you guys to do that. I really want you guys to work through the steps. So, so we're going to go through this step, which, for all its issues, it at least helps us break it down. Right? And this is where the triethylamine comes in. So this is what I was mentioning earlier, right? We have our chloride ion. If we were doing kind of our so-called bookkeeping method, you'll see that the chloride will deprotonate, and then you have HCl. You can imagine that in the actual chemical reaction, you know, as you're generating something reactive like HCl, that's going to potentially cause problems. So the triethylamine is kind of in there to buffer that and to sort of make sure that you don't generate HCl in the reaction. Make sense? You'll find sometimes people will say that you can deprotonate that first. This is a situation that I would be okay with that, because you might say, I don't like that at all, so I'm going to take triethylamine and make the alkoxide. I don't like that one either. We're kind of stuck in a situation where I don't know which one's the lesser of two evils, but we do know that the reaction works, and so either one that you want to do is fine with me. And then we get here, and you do use an excess of triethylamine, I think usually 3 equivalents, just to have excess. I'll just say excess. And so, you know, the final mechanism is the one that I sort of was talking to you guys last class about, and was saying how it's basically it's an elimination reaction. It might look a little bit different because we're so used to seeing elimination reactions making alkenes, right? In this case, our leaving group is DMS. Right, rather than halogen or something like that. But it's at its core, if we sort of just focus on the electron moving and forget about what the specific atoms are, you know, there is that analogy. It's really analogous to, you know, an elimination. And just to sort of point it out again, right, our classic elimination reaction is base. Right? If you want to do anti-periplanar to be, I didn't really show it there, but if you really want to start showing anti-periplanar nature, so you see that there's the parallel that it's kind of an elimination reaction. So, okay, Olga, does that help a bit? Just breaking it down a little bit like that. Okay. All right, so we've got about any questions? Okay, so we've got about. I'm just gonna sort of go through the rest of the reactions in chapter 11 today, which we should have no problem getting through. And we're moving along. So I want to start with a question for you guys, which is to say, you know, in it'll be videotaped. It was giving me issues, but it's there. So, you know, something we were talking about earlier, right, is that you know, alcohols are kind of versatile, and because of that versatility, you know, they can be deprotonated, they can be protonated, they can be served as nucleophiles, they can effectively be turned into electrophilic sources. So they have this versatility. That versatility then, at the same context, can oftentimes pose challenges when you're trying to do, say, for example, multi-step synthesis, right? And so one of the things that sort of we want to sort of keep in mind is that a lot of reactions that we've learned, right, may start to cause problems when we have alcohols around. For example, let's say that we wanted to do this reaction where we started and we treated this molecule, we wanted to deprotonate this guy here. Right? How do we deprotonate an acetylide? Yeah.
NaNH2?
Yeah, so we would start with NaNH2. And it's a one-pot process, so when we do one-pot processes, we go with these Roman numerals. instead of 1 then 2, so it's I, because we basically add sodium hydride, we let it react, and we add in an electrophile, and let's just say our electrophile is bromethane, right? H3CBr. And what we would anticipate to get, right, would be, what we'd be trying to get is this, right, once. But, bless you, but what would be the problem here? There's a fundamental problem. We might want to get that, but we might not get it. Rachel. Say again? So leave with it. I don't like that term, but it would prefer to react, given the options, it would prefer to deprotonate the OH right over the H. Right? pK of the acetylides are in the 20s, right? pK of an OH is going to be in the teens, right? So given the two options of whether sodium amide is going to deprotonate this versus this, it's going to choose to deprotonate this. And then you may say, well, Professor Morelli, what if I use an excess of NaNH2? Well, then it's still going to cause problems because you may end up then getting a mixture where you get some of the ether as well, okay? So fortunately, alcohol chemistry, because of its importance, there's a lot of ways in which people have learned to use this sort of idea of protecting groups. So you sort of protect the alcohol with something, right, so that you can do your chemistry, and then you deprotect it. So basically, you do a reaction to shield the OH, right, and then you remove that. And in order for a protecting group to be effective, right, you need that protecting group. Good protecting groups would be something that wouldn't be harsh to put on, right? If you're going to invest this time putting something on, you want it to be high yielding. You don't want it to disturb other reactions. And then when you take it off, you also want that to be sort of mild. And so these two sort of things can kind of be a little bit at odds with one another. If it's easy to put on, right, for that same issue, you would think it would be hard at the same time to take it off, right? So this gets this sort of idea of orthogonality and having a protecting group that might be special and work under an environment that may not affect too many other things. And really the go-to protecting group for alcohols, certainly not the only one, but one of the big go-to ones is silyl protecting groups. Okay, so what you do, turns out there's a whole bunch, I'll just say R3SiCl. Depending upon what the R groups are, there's some versatility here. If it's a trimethylsilane, those are a little bit easier to put on. They're a little bit easier to put on, but they fall off really quickly as well. So you kind of want something that's going to be, maybe that's what you want. The classic one is TBS, which is diterbutyl. It's also TBDMS, so it's diterbutyl methyl. This is TBDMS. Tertbutyl, wait, sorry, got that back. Tertbutyl dimethyl, sorry. Tertbutyl TBDMS. So TBDMS, sometimes just called TBS, just two different terms that are used. So you'll see this a lot. So TBDMS, tertbutyl, D is dimethyl, DM dimethyl silane. TBDMS chloride, okay? And then you use triethylamine, and that will put on your silyl group. And again, I don't know that we necessarily need to go through the mechanism of this, right? You guys could probably figure this out, right? The OH, first step, what's going to happen? The oxygen is going to attack the silyl and kick out the chloride. Right? Second step is going to be, again, just as I said before, scavenge the HCl rather than the chloride deprotonating alcohol. You've got some triethylamine in there to do it. So this is stuff you guys should be able to figure out. Okay, now we can go ahead and do our chemistry up here. So this isn't going to work. So but we do this. then the final step that's kind of important is you have to be able to take off the silyl group. And in order to take off silyl groups, it's something that is fairly unique to silyl groups, and it's fluoride sources. So usually just F- of some type. There's a variety of different fluoride sources that people will use. Under more acidic conditions, sometimes people use HF, which for obvious reasons isn't something that people like to use that much. We were saying how dangerous it is. HF pyridine is kind of a buffered saltish, which isn't really that great either. Usually what people like to use, and what I'll tell you guys, is TBAF. I think the book discusses it. So TBAF is a salt, is a fluoride salt. It's a tetrabutyl ammonium salt. Okay, so that's tetrabutyl ammonium fluoride. Okay, it's a salt, but you also notice that it's very greasy, right? So similar to like what we were talking about with PCC, even though it was a salt, it had this sort of the greasy pyridine, which made it organic soluble. So TBAF is a organic soluble form of fluoride source, and the fluoride will basically pluck that off, and then following an aqueous workup, right, you're going to end up getting your product. So you do the TBAF, you'll probably end up with the ammonium alkoxide salt, and then following an aqueous workup, you'll get that. Okay, does that make sense? Yeah.
Are we going to need to know the mechanisms for that, or just know that?
So okay, so the mechanism, if you're asked for TBAF mechanism, you know, or an HF mechanism, well, an HF mechanism would be very similar to ether. You know, like if you take an ether and you treat it with HBr, right, as we were kind of discussing a couple classes ago, right? Ether with HBr, same thing as water with HBr, right? You'll cleave it and you'll end up with ultimately bromides on both sides. So if it's HF, same thing, right? You protonate the oxygen, the fluoride would come in and attack. In the case of TBAF, it's not really an acidic media, so unless you're running it in like a, sometimes people run it as like a water THF mixture or something like that, but if you don't have any other proton sources, then the fluoride is just going to kick it off. You're going to be left with the alkoxide until you do the aqueous workup at the end. Does that make sense? So the fluoride will just right, generating the alkoxide, aqueous workup will then protonate it. Make sense? Okay, so this is a protecting group strategy. Keep this in mind for synthesis problems in particular. It could be valuable. You know, this is the type of thing where if you're you know, you have a synthesis, you know, and you have to pay attention to, is this going to be deprotonated? Is, you know, yeah, Claire. Because there's a lot of different sources of fluoride. So I'm just saying fluoride, I was saying HF could be the source of fluoride, tetrabutyl ammonium fluoride, HF pyridine fluoride. Basically, it's the fluoride that's important. And the reason is that a fluorine-silicon bond, please don't, I didn't look this up beforehand, I forget the reason why, but it's a very, very, very strong bond. Fluoride has, I forget what the, if I could look it up, I should probably look it up beforehand, but it's just a very, very, very strong bond. So thermodynamically, it's driven that way. Yeah.
Almost any source of fluoride is fine.
Yeah, I mean, one of the big, just for reference, yeah, so any source of fluoride is usually fine. One of the things with fluoride that's kind of interesting, that puts things into perspective, is that like when you're running these reactions, you often need like special glass, right? Because the affinity of the fluorine for the glass, right? Because glass is made of silicate, right? So you'll like etch. Like if you go into our lab and you look at our flasks, you'll know which ones TBAF was used in because there'll just be a film. It's not a film; it's just etched area that's where the solution would have been. So.
What is the code?
This, that's basically just up there. So same stuff is up here. Okay. Okay, so that's silyl protecting groups. Okay, we'll learn about one other, maybe learn a couple more protecting groups, but this is kind of one of the major ones, and the one that I think most people tend to remember pretty well. Okay, okay, so I think that's it for sort of that. I think we can go on to epoxides. All right, so let's head over to epoxides. So if you guys recall, epoxides, we talked about them maybe a little bit last semester, and sometimes you hear about them, but let's talk about them now. So this is an epoxide. It's a type of ether. It's a three-membered ring, 2 carbons and an oxygen. You can imagine that it's highly strained, right? It doesn't, three-membered rings it's not really matching the bond angles that a tetrahedral, bond, an sp3 bond would want to have, right? So there's a lot of strain built up, and so there's a lot of energy. And so reactions with epoxides, as we'll see, are very, they're oftentimes highly thermodynamically favored, right? So the formation of epoxides, we'll show a few ways that you can make epoxides, and then we'll talk a little bit about how epoxides can react and be a synthon. Okay. So perhaps the easiest and one that I think you guys could probably figure out. I mean, a lot of them come from alkenes. Maybe I'll use this as an opportunity to discuss stereochemistry really quickly. But one of the ways that you can sort of make epoxides is from sort of a 2-step process based upon chemistry that we've basically learned already. Okay? And the first step is going to be basically chlorine or bromine, and we'll just say chlorine and water. Right? And then the subsequent step is going to be like sodium hydride. Okay, and what's going to happen is, and we'll discuss this in a moment, what the stereochemical outcome is going to be. But we're going to get an epoxide. And I haven't shown stereochemistry because I want us to discuss the stereochemistry as a class. Okay, so this is an organic 1 reaction, part 1. Do you guys remember what the stereochemical outcome of this is? Yeah.
Anti-SCl and OH.
Right, so it's going to be anti. If we go through the mechanism of it, we'll remember that the chlorine, particularly the bromine, I don't usually talk about the chlorine that much, but it's a little bit smaller, right? But yeah, I like it a little bit better with bromine, but whatever, this is what it is. Usually we think about bromonium, so you can imagine the same thing with chlorine. Right, but you're going to get that sort of backside attack, as was said, right? And so ultimately the product that we're going to get after step 1 right, is going to be following loss of protons, so we want to go through the whole thing. Right, generate HCl. Oh. All right, we'll get our alcohol, right? And so now if we take this molecule and we treat it to the base, right, what's going to happen, right, is we're going to get, in essence, backside attack, right? So let's think about the stereochemistry that's going to lead to, right? So this is where I think thinking about stereochemistry is important. Okay, I'm going to draw, it's oftentimes very helpful for me personally to draw on all my stereochemistry as I start to think about this, right? But basically the chlorine, think about where that sigma star is, and it's right behind there. It's very, very, very difficult for me personally to look at this structure right here and to be able to immediately tell you guys what the stereochemistry is. I don't think it's as obvious. I think that you've got a 50-50 shot of being right, so you might look at it and you might say, oh yeah, I know what it is, and you guess right, and you think that you've got this intuition. I oftentimes really need to draw structures in a way that helps me visualize where the bonds are coming from and sort of put it into a way in which case I can see it more. And when I'm seeing electrons being pushed, seeing them come this way is difficult, right? It's hard enough to see molecules and think of molecules in 3 dimensions, to think about a moving set of electrons in the sort of Z-plane becomes equally difficult. So what I generally like to do, and this goes back to how I really push you guys in the stereochemistry chapter to redraw molecules and get good at that, I like to redraw this so that the chemistry is going to be in the plane of the board. Okay? So I want to draw this molecule. I want to redraw this with the oxygen in the plane of the board. And I want to draw the chlorine down there. Okay, does that make sense? I want the chemistry in the plane of the board. I want, when I deprotonate that oxygen, I want backside attack. Okay, so my oxygen is going to be coming from the back face. And then I'm going to fill in everything else. Right? Then I'm going to fill in everything else because everything else is going to stay in the same place. And so, haven't thought through this yet. What is this? What is this? What is this? What is this? But rotating the molecule around, we should be able to see this. This is, are you guys following? Right? It's a little bit easier to see it in the plane of the board rather than trying to go from here. Maybe you think that you can see it, but sometimes it's challenging. Okay, so if I want that oxygen up in the plane of the board going up, what's coming towards you guys? Yeah, so I'm gonna, so effectively what I'm doing, right, and sometimes it's difficult to go immediately there, so sometimes it's good to go 180 degrees and back, but you guys should be able to see this, right? The hydrogen, the OH is there, it's gonna come up, right? Which means the OH is there, it's just gonna come down, right? Which means the R that's in the plane is just gonna move this way a little bit. So right, so the hydrogen's gonna be here, the R group's gonna be there. Chlorine, same thing. Now we're moving the chlorine a little bit further. The chlorine's going from there straight up, okay? Since this is going up that way, the hydrogen, right? Sorry, I lost me. It's hot right now. I went in the complete wrong direction. I was looking at the sigma star, and I started moving towards the sigma star. Sorry, no, we want it to move down, right? I was looking at that. Sorry, just a little bit Freudian. So the chlorine is moving down to here. My bad, that's why I lost you, Claire. The chlorine is moving here, right? So if the chlorine is just moving down a little bit this way, that means the methyl group in that same direction is going to be towards you, right? Right, and the hydrogen is going to be going back, okay? Which basically means that when this bond forms, and we lose our proton, we're going to have the epoxide, right? And the things that are in the front are going to stay in the front. The things that are coming towards you are going to stay coming towards you. Things that are going away from you are going to stay going away from you. And so the methyl group and the hydrogen are going to be there. And again, I think it's just a good practice to draw it this way. It helps make sure that you don't make mistakes. You know, you might look at this structure here, right? And you might say, well, I've already got the R groups in the same position. I can backside attack and I can see it. And that may be somewhat right, but I'm not sure if it's right for the right reasons, right? It may just be coincidental. And so I think it's always really helpful to think about sort of backside attack. Where is that sigma star? How do we line it up and how do we see it? Yeah.
What's the H on the O?
So that's the second arrow. So once it attacks, so the base is sodium hydride.
Yeah.
So the first step in this is going to be forming.
Yeah. I use sodium hydroxide for that, or it has to be hydroxide?
Sodium hydroxide. It might be okay in some cases. Sodium hydride is usually the reagent that we use. Sodium hydroxide would probably be okay. I'm not sure. But now we have this. I don't know. Now I have to redraw this again. But okay, so and then we see that the R group and the methyl group are on the opposite sides. Oops. Oh, when did R here become a methyl group? Sorry. So the two R groups are on opposite sides of one another. So at the end of the day, you know, the structure. I mean, whatever. I guess it's just what I drew before. So it's, I guess I just drew kind of the flipped version of it based upon what we saw, right? Where the two R groups are on opposite sides. Same thing, just flipped over the other way. So the important point is that we have the two R groups, and they're kind of across the epoxide from one another, okay? So the important point here is that there's a stereochemical outcome of the epoxide, right? And that's going to be dictated based upon what the stereochemistry of the alkene is. So we did the same sequence, and we did the cis alkene. What we'll see is that we'll get the opposite epoxides, okay? Does that make sense? Okay, and you can work on that one on your own.
So
Yeah.
trans alkene creates trans epoxide.
Yes. Okay. All right, so a more direct way for epoxidation is with the use of MCPBA. Okay, so you can actually get to epoxides I'm just redrawing stuff that I already drew. Sometimes you'll see a reagent called MCPBA. Okay, so MCPBA is a peroxybenzoic acid. So learn about aromaticity. The M technically stands for meta, so it stands for metachloroperoxybenzoic acid. I don't understand why metachloro is the one that's used. I'm assuming it's a stability issue, probably a little bit heavier, which when you have something like a peroxide that might explode, maybe just having a little bit added mass on it may help. I don't know, I'm guessing. Maybe there's an electronic, I have no idea. But this is one of the go-to epoxidizing agents. The peroxybenzoic acid, right, a benzoic acid, benzoic acid is right, so this is benzoic acid. And it's the carboxylic acid. Peroxybenzoic acid is basically, it's the peroxide version of it. Okay, and so this is an oxidant that is what we sort of consider an electrophilic oxidant, meaning that it will react preferentially with electronically rich alkenes. Okay, and we can think about that in a way because the sort of the benzoic acid part of it is kind of almost like, as we'll see, is kind of like a leaving group, and it's sort of electron withdrawing, and so it's sort of an electronically poor source of oxygen. The mechanism is a little bit more complicated. Bear with me. Aromatic over here. So when you have peroxybenzoic acid, it's a net neutral process. You actually generate benzoic acid throughout the process of the reaction. But what's going to happen here is the MCPBA sort of forms this 5-membered hydrogen bond, right, where the lone pairs here form a hydrogen bond with the OH. You guys see that, right? And it's actually a concerted process. So there's going to be a lot of arrows that I'm going to be drawing here, but it is a concerted process. Okay, and so what's going to happen is the electrons that are in here are going to attack that oxygen. Okay. this bond here is going to break. Okay. This bond here is going to, instead of a hydrogen bond, it's going to make a full-blown bond. Okay. And notice when it does that, now that hydrogen has too many bonds to it. Right? So we've got to finally break that last bond, and where's that going to go? Right back to the other carbon. Okay? So basically what's happening here, right, is you can sort of break this down mentally in that it's sort of a double bond attacking, right, leaving behind a positive charge here, right? Just trying to think if there's a way that I can maybe break this down for you guys. Let's maybe try to break it down. Do this. So it's a conservative process, but I'll show it a little bit stepwise, maybe just to help you guys see what's happening. Right, so if we picture this attacking, right, when the alkene, you guys can see this, when the alkene attacks that oxygen, this is just breaking it down stepwise. We're imagining attacking the OH, right, and kicking off the acetate group here, the benzoate group, right? That's a typical alkene reaction. We're leaving behind a carbocation over here, right? That carbocation, in essence, needs to shut down. So I showed it here just in that process. I'll just go more direct just because this has a negative charge on it. Those are resonance forms. And that's going to sort of help form it. So the real mechanism is concerted, right? But I recognize there's a lot of arrows that are going on there. Maybe just breaking it down to 2 steps might help you see that it's the alkene sort of behaving as a nucleophile, right? And then kind of the acetate deprotonating the resultant alcohol to shut down the epoxide. You guys see that? Okay. All right, so this is the other way that we can make epoxides. The book has a, I'm not going to teach it because we don't have time, but the book has one of the very classic examples of what we call asymmetric catalysis, called the Sharpless epoxidation, which is it's a variant of this. I'm not going to talk about it too much, but I'm not going to talk about it at all, actually, but it's just sort of worth mentioning really quickly that one of the sort of very early, right, so you guys know from last semester that chirality is really important, right? The classic thalidomide example, a drug that one enantiomer did something good, the other enantiomer was catastrophic, right? And so one of the overarching goals of synthetic chemists is to create molecules that are a single enantiomer, right? And one of them. And so this case it's non-symmetric, but you can imagine that we could potentially be generating stereochemistry throughout this process. And depending upon which side of the double bond is attacking and is getting oxidized, you can generate one of 2 enantiomers. And so the Sharpless epoxidation was one of the early methods that people had really come up with for sort of catalytically generating either one enantiomer or the other enantiomer. So it's a fairly powerful reaction, but we don't cover it, but it's worth mentioning more as a historic sort of comment to make. If I were to really want to make you guys not pay attention to doing anything else, I would show you the transition state for that, which the book doesn't have, and I would be tempted to show you. And so to make sure that I don't tempt myself, that's all that I'll tell you about the Sharpless epoxidation. Okay, so all right, so let's talk about chemistry of epoxides. So as we sort of stated, epoxides can be really versatile building blocks. But based upon what you kind of start with, you can imagine scenarios, for example, where you do your epoxidation, say MCPBA, you get your epoxide, and right, we unlike the previous case where we had a symmetric epoxide, here we have an unsymmetric epoxide. And so what that means is that if we're going to open this epoxide, treat it with some type of a nucleophile, we can imagine that nucleophile attacking on one face sort of or the other face. And it turns out that how you sort of mediate these processes will actually have fairly different results. Okay? So if you were to take an epoxide, I think what I would predict you guys might be able to sort of figure out even without me telling you this, so I'll test you here, is if I took this molecule and I treated it with sulfuric acid and say methanol, something like that, right? And we were to start to ask the question of what would happen, we could potentially use mechanistic intuition to try to explain what might happen here. So what might happen if we were to take this stuff, this sulfuric acid, and this epoxide? Rachel?
I think that we were talking about
Well, hold on. No, I'm just asking the mechanism. What's the first step? Constantine.
The oxygen would coordinate.
Yeah. Yeah, so we only really have one set of lone pairs on here. So as Constantine said, we're gonna those lone pairs are really our only option. Again, protonation, deprotonation is all reversible, but in this case, that's our only real lone pair. And from here, there's something that would be bound to happen fairly easily, right? What would that be?
Ring open.
It's going to ring open, right? And so if we think about that ring opening forming, right, we can open one of two ways, and this is analogous to what we've seen before, right? We can open to have we can open up to have a tertiary carbocation, or we can open to have a secondary carbocation, right? And given those two options, right? Given those two options, what do we think would happen? Yeah, right? I mean, we if it was an alkene, we'd know, right? And this is the analogy, right? Given the options, we're going to open one way. Now, remember that none of these is kind of, to a certain extent, similar to the bromination. When we're dealing with these sort of intermediates, I'm hesitant to call these kind of resonance forms of one another, but they kind of are, right? Usually we reserve the term resonance form to non-ring opening and so forth, but these are kind of resonance forms, right? We can imagine, it could be this way, it could be that way, it could be that way, and if you had this molecule and there was billions of them, maybe most of that billion would be here, a decent percentage would be here, a little might be over there, right? But it's really a conglomerate of all of it. And truthfully, as I'm saying, I don't know necessarily this would be where all of it would be, right? Because we don't really have a full octet, right? The one that we have, the full octet, would be this one up here, right? But, much like the bromonium, the nature of this being more likely than this has an impact on the overall electronics of this system, right? Which basically means that the delta plus, right, much like with the bromonium ion that we saw, right, that delta positive is going to be mostly on that guy right there, right? Which means, right, that if methanol were going to attack, right, we may get some stereochemistry here, right? We may get some stereochemical preservation, if you will, right? So it's an acidic process. There's cationic media to it, but in part because of this sort of memory, almost in a way, of chirality, right? The methanol can sort of do a pseudo backside attack, right? Which means that the methanol adds in, right? We're going to get inversion. Did you guys see that? How when the methanol adds in, it's sort of, I'm not going to call it an SM2 because it's not. It's more memory of chirality. But there will be a inversion of stereochemistry that's at least consistent with an SN2 reaction, although it's not an SN2 reaction. Does that make sense? I got to choose my language carefully there. Okay. And then so the product of this is going to be OMe. And so this is going to happen with, anytime that you have, we think back to our chemistry with alkenes, right? Where we added, under acidic conditions, we added things across alkenes. All those things that we sort of saw under those acidic media, say for example HBr, you could probably guess what's going to happen, right? The bromine's simply going to take the place of the methanol, right? Any alcohol would do this. And in some other cases, sometimes people will pair maybe a Lewis acid with some weak nucleophile that's a carbon-based one that we won't get into and do it as well. But the point is that when I think the broader point here, I'm showing one example here of a reaction, but the broader point that I want to make is that this is an example of acid-catalyzed ring opening. And the acid-catalyzed ring opening will get to this sort of dynamics here, right, which will ultimately lead to the nucleophile attacking the more sterically, I want to choose my, it'll end up attacking the carbon that would otherwise have the most stable carbocation. Let's put it that way. Okay, does that make sense? Okay. Conversely, what are we doing with time? Do one more thing I want to discuss. Okay, so conversely, this is what happens under acid-mediated ring opening. Okay. If instead of, say, for example, acid and methanol, just use a parallel, if we use methoxide, we could potentially get elimination, but let's just stick with this for consistency's sake. This might not be as good of a reaction, but I think it'll be okay for now. If we wanted to use the methoxide as the nucleophile, right, now it's not going to be electronically driven because it's going to be based upon less based upon those electronics and more based upon sterics. Okay, and so this is one of the things about epoxides is under activation of the epoxide through Lewis or Bronsted acid, you get the regioisomer I showed you previously. When you're using a strong nucleophile, I'm showing methoxide. Usually we're talking about things like sodium hydride or sodium borohydride. Methyllithium is a good example. I'm just showing sodium methoxide here as kind of an analogy to what we saw before. But usually we're talking about better nucleophiles, things like methyllithium and so forth. But in that case, right, we're going to get the addition, as you might imagine. Certainly we're going to get following the aqueous workup. So we're still going to have the anti-relationship, okay? But where the methoxy is going to end up is going to be different, yeah.
So this one attacks, because this one's more of like a backside attack, that's why it's less substituted.
Yeah, this is pure SN2 chemistry. This is exactly SN2, yeah. Okay.
And this is because it's not acidic?
Yeah, so it's whether it's driven by, so at its core, are you activating the epoxide or are you using a strong nucleophile? Does that make sense? So if you're activating the epoxide for ring opening, that's where it'll go sort of more Markovnikov type, right, for lack of a better word. when you're using a strong nucleophile and it's driven by a strong nucleophile, that's where it will be sort of more quote unquote anti-Markovnikov-like. Does that make sense? Okay. All right, so let me just finish with sulfides. Okay, so the last thing that we'll discuss will be sulfides. So if you look on the periodic table, you'll see that right below oxygen is sulfur. Okay, and so many of the same reactions that, well, not many of them actually, it's completely different, but certainly when we think about alcohol chemistry and we think about deprotonated alcohols and using them as nucleophiles, one of the classic things that we learned from substitution versus elimination, right, was that sulfur thiolates, right, are actually really good nucleophiles. They're not as basic, so they're less prone to do acid-base type chemistry, but they're really good at behaving as nucleophiles. So as you might imagine, if you were to take a thiol, right, so that's a thiol, that's what we call thiol, and we were to treat that to sodium hydride, right, we would get what we call a thiolate, right? And then this can serve as an electrophile. Sorry, nucleophile, right? So if we take that and we treat it with, if that's R1, if we treat it with R2, bromide, right, we can generate what we call a thioether. Sometimes referred to as a sulfide, colloquially referred to as a sulfide. I'll probably just call them thioethers to stay consistent with the terms. Now, one of the differences between thioethers and ethers is that, as we've sort of spoken about the octet rule, right? When we're talking about the octet rule, we're really only talking about the second row, right? We're talking about boron, carbon, nitrogen, oxygen. The moment that you drop down, if you think back to Gen Chem, right, and we're doing our sort of, our counting of 1s, 1s1, 1s2, then we go 2s2, blah, 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 right? If you remember, when you get to the sort of the transition metals, the first of the transition metals, if you remember, there's that weird number switch where you start as 4, and then you drop down to 3 for the d orbitals.
That's the chromium and the manganese.
So that's like exactly, chromium, manganese, iron, So that row right there, you're sort of at the 3D, and one of the things about that is that it's sort of third row. You're kind of in a way, I guess, talking about the energetics of the third row, and so the fact that you've got sulfur, phosphorus, chlorine, silicon can actually go up to hypervalent. So a lot of those atoms, they can break the octet rule. The octet rule doesn't apply to them per se, because they can actually, although I still think it's a bit sort of debating what the exact reason is, people have at least come up with the rationale behind it. The way that I've always reasoned it is, you can sort of get some contribution from the d orbitals, right? I think that's usually what people think about it. So you can get to, that's the whole reason why sulfuric acid, right? We've already seen sulfur break the octet rule when we draw sulfuric acid, right? So what that means is that if you were to take an epoxide and you were to treat an epoxide with an oxidant, nothing's going to happen. If you were to treat sulfur with an oxidant, you can get to sulfoxides if you oxidize once, right? So DMSO is an example, dimethyl sulfoxide, right? That's once. And then if you oxidize again, sometimes you'll see this drawn as a double bond. And then if you oxidize again, you'll get to what we call the sulfones. I'll just draw it this way. Okay. Now electronically, yeah.
Wouldn't that be 2 more levels of oxidation? Because you're going from 2 bonds to an oxygen to 4 bonds to 2 bonds to sulfur to 4 bonds.
So it's a resonance form. It's you can draw either one. So this is 1 plus 1 minus 1, which can be drawn as this. It's the same thing. So it's the same. Oh, am I understanding you? I don't know.
You're going from the oxidation of because sulfur each time it's attached to an oxygen is like a new oxidation state. So
Let's not. So you're comparing it to metals. Sulfur is not a metal. So yeah. Let's not. I don't even want to go there. So it's DMSO really looks like that. We oftentimes draw it like that. DMSO here may be better associated like this, but it's generally drawn this way. So it's a little bit more complex, and it's not necessarily an apples and apples comparison with transition metals and to talk about the oxidation of it. But it's kind of sometimes hard to control this oxidation. These will generally, under enough time, even with similar oxidants, like the book I think discussed, what did it say? It's like hydrogen peroxide, I think it discusses. Somewhere in here. I swear I saw it. Whatever, right? It's like basically hydrogen peroxide, I think is the one that usually goes here, and stronger oxidants like NiO4, like periodic acid, and sodium periodate will actually oxidize all the way to this sulfone. What do you guys think? And there's something that's important about this, and I'll maybe show an example of a paper that's about to come out in our group that is not here today. He was here last time. So one of his PhD students in my group's got a paper that's coming out that takes advantage of this chemistry a little bit. So what's the oxidation? What do you think the impact is on, say, for example, R2 electronically? When you go from this to this, what's the nature of that sulfur? It's losing its electrons, right? It's getting electrons pulled away from it, right? It's getting pulled in this direction. Then you go to a second one, it's getting even more electronically pulled away. So the impact on the electronics of molecules based upon the change of this system can drastically affect this. So do we have time, actually? Maybe I'll show you guys this. Yeah, we got 10, 15 minutes. So let me show you, I think that's it for the chapter. Let me actually show you guys where we have a paper that's about to come out that actually took advantage of this oxidation chemistry. So in my group, one of the projects in my well, really the sort of bread and butter of my lab, at least to date, has been. So anybody that's taken organic already, we'll learn about aromaticity shortly. This is sort of a tropone. It's when you have a 6-membered ring with a carbonyl there. It's an aromatic system, which we'll get into later on. Just keep in mind, it's like benzene. It's planar. It's flat. Our group has been studying these sort of oxygenated versions of these, sort of called alpha hydroxytropones. They're fairly acidic. Why do you think they're acidic? Yeah. Exactly, right? The moment that you deprotonate this guy, this is sort of like it's kind of like an extended carboxylic acid. You can push those electrons all around the system and go up into the carbonyl. In fact, tropones are often drawn as a resonance form. Like this, where you actually will simply move the electrons up there, and then you have sort of the pi system here. Okay, and that speaks to potential Lewis basicity of this system anyway. So the pKa of this is like. So the first pKa is like of this molecule is say pKa1. We did study the protonation. Actually, undergrad did these pKa studies in our lab. John Stasiak, who's just starting his PhD work at NYU. And so the parent tropone, the first pKa of the parent tropone, so carboxylic acid's pKa is like 4, right? Like acetic acid is like 4 or 5. Phenol, like benzene with an OH, is like 10. Tropolone This is trobolone, or the trobolone deprotonated. That's got a pKa of about halfway in between. It's about 7. This pKa, I think we measured at like 6.8 or something like that. All right, hold on, sorry. If I'm going to do this, let me do it right. Okay, so then if you can deprotonate it again though, right? And that pK, so you can deprotonate a second time. Okay. And so this molecule here, the pK of this is like, I think 11.6 or something like that. pK. I think you measure about 11.6. I'm guessing there. You can read the paper. But basically, you can deprotonate this twice. And one of the thoughts in our group is that, and we did some of these studies with Emilio Glicchio, where sort of one of our theories has been that, you know, the way that these molecules bind, they are really good drug fragments for sort of metals, or sort of metalloenzymes that have 2 metals in the active site. And the kind of idea that we've had is that the molecule wants to adopt this diionic form, right, in order for it to be able to chelate. And so, as I was talking to Emilio about this, he sort of was calling it sort of an ionization penalty, right? It's got to adopt that diionic form, right? But to do that, it may have to leave what it would ordinarily want to be in the physiological pH, right? So this is what it's at physiological pH, but when it binds, it's going to maybe look something like this. And so there's an equilibrium problem there, right? That where it wants to be in this form to bind, but it wants to be this the other way. So one of our thoughts was, if we could, at least with our current SAR, one of our hypotheses has been that as we bring substitution on these systems, we can actually bring that second pKa down. Does that make sense? So if we bring in substitution here, we can alter that, drop it down, and if we can get it closer to physiological pH, we'll pick up a little bit of potency towards our targets. Okay? And so, Nana, not here. Who's got Nana? Okay, so those of you that have Nana developed some chemistry. Nana Agyeman. He developed some chemistry in our lab where it'll become maybe a little bit more clear the early part of the chemistry once we get to aromaticity. But basically, he took these molecules, he treated it with NBS. Right? You guys remember NBS? Right, so he would heat this with NBS and benzene, and what he'd end up getting is he'd get a mixture of molecules. Right, where you'd have a single bromide, bless you. Oops. Okay, so you do this. Okay, and so you'll be asked this mechanism question after exam 2, maybe.
Directing group, right?
What's that?
That's not aromaticity, that's not directing group.
It's not a directing group per se. It's sort of pseudo. It may be electronically driven, but it's a non-selective process. We don't quite understand why this has been precedented in some studies by another group before us on closely related systems where after you brominate it once, the second bromination's, for whatever reason, is kind of fast. It's weird. It's not quite sure why. Well, he can isolate these. He generally doesn't. He then took these molecules and he treated them with some violates. And the violates did what we'll see is sort of nucleophilic aromatic substitution, which will become something that we'll see in a month or so. But you could certainly just imagine how you take the thiolates and you treat that with these without thinking through the mechanism per se. You can imagine that those thiolates will replace the bromides, right? Makes sense? Even if you can't draw the mechanism, we see a nucleophile, we see a leaving group. That mechanism will become more clear when we discuss nucleophilic aromatic substitution. And so he was able to get to a series of molecules like this. And then he would usually separate here. Right? And so he would basically do that. And then what he did, so he was basically able to take it through one reaction, and then he was able to, after that second reaction, he separated it, and so it's kind of a divergent route. So we were interested in these for drug development standpoint, so we took this molecule, would treat it with various phthalates, and he would get 2 new hydroxytropanones, right? We're interested in modifying these molecules and seeing if that'll improve their biological profile. He would do this, then he would get 2 molecules, right? He then took these molecules and he oxidized them with, I believe, MCPBA. I can't believe I'm not remembering. We just submitted this. So I believe he took it and he treated it with MCPBA. If he was here, he could tell us. And with MCPBA, right, he was able to get the sulfones. Okay, so basically, we kind of liked this. We thought it was nice because from a kind of a library generating standpoint, as you're trying to test these molecules for their activity, right, so we kind of like this because basically from one of these, in what amounted to really 3 steps, we were able to generate 4 new substituted and functionalized hydroxytropanones. And what we did was we took advantage of the fact that from these molecules, we can in fact change the electronic properties, right, of the tropolone itself. And so if we think about, you know, the pKa, for example, or if you think about the electro, you know, like the electronics maybe of this system there and how electron deficient that might be, he was able to make several of these. Again, without going into depth on the biological data, we got some really nice biological activity that really showed a dynamic range of bioactivity. Henry?
So that by forming that, sometimes in a new molecule prevents like the
Well, so I'm going to get to that in a second. That's what I'm going to leave you guys with. So that was the thought. That was the driving force behind this. It was specifically driven by hepatitis B. So we've got studies that are ongoing with a collaborator at St. Louis University where we're trying to develop novel hepatitis B antivirals for curative medicine. So that was what actually drove these studies because our understanding of our past data suggested that maybe this strategy would work. It didn't. We got decent molecules. We actually found a lot better hits by sort of repurposing the library, so taking the library and testing it versus different diseases. We got even better results for other stuff that we weren't planning on. It's been the way I work, right? It's like I try to do this one thing and get it in the right hands, and they find some use of it. So I just keep going. But what's interesting, is the pKa, right? So what I thought was fascinating is these molecules here that had dropped the pK dramatically had practically no activity for anything. And we have to do a little bit of follow-up studies on it. We've done a little bit, we tried doing a little bit of biochemical testing to sort of test this hypothesis, but it was inconclusive. But that second pKa, like you don't see that big of a change of that second pKa really for any of these. You see a bit of a change for the first pKa, but that was never part of our hypothesis. It was the second pKa. And the only molecule that had a dramatic drop of that second pKa of these was this one with 2. And it dropped all the way from 11.6 down to about like 7.4, 7.5, right? And that's just in our assays. So we speculate that it may be the case that these molecules, we don't want them to be too acidic, right? Because if they're too acidic, then they might be dianionic at physiological pH. If they're dianionic at physiological pH, they might not get into the cells. So cells are generally, you want them to have a little bit of grease to penetrate the cells. But if it's too charged, sometimes tough to get in. So that's our hypothesis. But so anyways, this is just an example of, for what it's worth, paper should be coming out soon if you want to read it. But this is just an example of where we actually use some of this thiolate and oxidation chemistry in our work. And from a mechanistic standpoint, you guys, by the end of this semester, so keep an eye on this, because this would be a really good, I think, question for exam 2. Not exam 1. Keep an eye on it. Keep that in the back of your memory. The paper will be coming out. So, all right. So with that, or maybe a final exam. So with that, I will see you guys on Wednesday. Yeah.
That knowledge